Okay, now we need to look at electrical vibrations, and in order to do that, I got to introduce you to some electrical components which you may not have played with before. So let's first of all say that on the web page here, on the WAMAP web page, under links, there is the FET Electricity Lab. You need Java to run this. Okay. Let's see here as it gets started. There we go. So this is a nice little lab, whatever, that I can play with. Can I change the size? Oh yes, I can. Okay. So first of all, there's the notion of a resistor. So I'm going to take a battery and a resistor and a switch. Switch. And some wires. Let's connect all this stuff together. Connect that to the switch over there, and then put a wire, come on, wire, onto this end, and there, and over there. So, here we go. When I flip the switch, power flows from the battery through the resistor and onward. Now, if I were to change this battery, let's change the voltage here. Let's up the voltage by some. What happens is, well, you see that the light gets brighter, and it makes it look like the electrons are flowing faster. I don't know if they're flowing faster, but it gives the notion that somehow that voltage is pushing the electrons harder, and that's the way I think of voltage. In fact, the letter that's often used to denote voltage is E, for electromotive force. That it's voltage you can think of as a force pushing electricity through the wires. Okay. So the resistor here resists that flow. If I were to increase, so let's turn the battery off there. Let's change the resistance. As I take that bulb and I give it more resistance, you can see it slows the electricity down. The light isn't as bright. If I make it less resistance, electricity flows faster and the light bulb gets brighter. In fact, if I take the resistance all the way down to 0, my components say, oh, that's just too much electricity and we're going to burn up, we're going to get too hot. So, okay, there we go. Slow things down. Okay, so there's the resistor. Now, let's take a look at what's next, capacitor. All right, so I threw away the last circuit and I grabbed a capacitor and another battery and a switch. And I got a light bulb up here that's not connected. But what I wanted to show you first is watch what happens when I close the switch here. What happened? Electricity moved really fast and it charged up that capacitor. Let's try that again. Let's slow it down some here. I'm gonna put a resistor in the way here. Resistor is just like a light bulb, although it's not gonna light. It's gonna slow things down. So let's discharge the capacitor here and try that again. Whoops. Yeah, never mind. Discharge the capacitor. And when I flip the switch down, you'll see that current flows for a moment and then it stops. The capacitor is as drawn, although there's a couple different types, but the way I think of capacitors is essentially two plates really close together. Electricity can't actually flow through it because it's disconnected. However, as an electron flows into one side, it pushes an electron out from the other side, up to a point where these plates can't hold any more electrons. You get a negative charge on one side because it's full of electrons, and a positive charge on the other side because it's devoid of all of its electrons. They got pushed away. So initially, it looks like current can flow right through it, but then it comes to a point where no current can flow through it. One thing you got to be careful of is that it actually stores electricity. Back in the old days of the TVs, you had to be careful that you didn't stick your hand on a, whoops, I don't want that. You gotta be careful you don't stick your hand on a capacitor because it would really shock you here. What I can do, let's remove that. I'm gonna put another switch in the system here. I'm gonna put a switch. Let's put it over there. Connect it with a wire. And another wire. So now I've got a loop here. And when I close that circuit, I can discharge that capacitor through the lamp. And did you notice at first it was very bright, and then it became less bright. So we can set that whole thing up again. Open this one. Let's reconnect that. That charges up the capacitor. Let's break that circuit here. So let's open up that. So there's no current going to flow through here. This is still charged. As I close that, it slowly lets out its charge through that light. You can see it light momentarily and then it goes away. So a capacitor holds a charge. Now, we need to talk about inductors. All right, I want to take a look at what an inductor does. An inductor, this little thing down here, I make it look like a coil of wire, and that's exactly what it is. It's a coil of wire. And when you run current through it, the coil, well, the thing is, anytime you run current through a wire, there's an electric field that builds up around the wire. When you coil the wire like this, and you get so it's going around and around, you get a bunch of strands all running parallel to each other. Then the magnetic field is amplified around the whole thing. So this is what we would call an electromagnet. As you run current through it, it generates an electric field. And the building of that electric field actually takes energy. So watch what happens when I flip the switch here. I got a battery over here, I got a switch right there, and I've got my inductor right there. So I flip the switch down, and notice that current starts to flow. And it gets flowing faster and faster and faster. What's happening with the inductor is that when you change the current, so you increase the current, you're building more electric field. Well, that takes energy, so it looks like a resistor. As the amount of change gets less, the amount of change in current gets less, and you're not building as much, and so it doesn't look like as big a resistor, and eventually it's going to look like a straight wire. In fact, if all I have is a battery connected one end to the other, I'm going to get a short circuit. So as this capacitor charges, not capacitor, sorry, this inductor charges, the electric field gets bigger and bigger. The current, although it's moving rather fast, it's not changing much. It's moving up slowly. And you get to a point where it's going too fast and there's too much heat and things are going to break. So let's take that down. Okay. Initially, it looks like a big resistor. As it builds the magnetic field, it looks less and less like a resistor and more like just a straight wire. Okay. The capacitor, remember, was the other way around. The capacitor initially had big flow, which then tapered off, right, to nothing. Where this one has very little flow, which then builds up faster and faster. So it does the opposite thing as what the capacitor does. Let me show you another thing here. As I got a light bulb up here. I want to attach the light bulb to the circuit parallel. So when I flip the switch now, the electricity can go two different ways, some through the light and some through the inductor. Notice throughout this, the light's going to stay the same brightness. It's not changing its resistance. But the more and more electricity starts to flow through the inductor because its resistance is getting less and less as the magnetic field gets built and then doesn't have to build more. And here we go. Now, what's not obvious is that what happens when you discharge, what happens when I disconnect it, what happens to that magnetic field? Well, that magnetic field collapses. Oops, I didn't get the, there we go, open up the thing. That magnetic field collapses, and what I'm allowing it to do here is discharging through the light bulb, right? Let me try that again. Okay. Charge things up here. Okay. So I'm gonna run some stuff through here. The magnetic field is building as the power is going through that inductor faster and faster as we build the magnetic field. When I disconnect the circuit, nothing can go here anymore. Nothing is charging that capacitor, so the magnetic field starts to collapse. The only place it has to go is through this way. It's going to currently, at the moment, the current is flowing from right to left. It's going to continue to flow right to left as that magnetic field collapses, and it's going to push the electricity back through the light bulb in the opposite direction that that light is, as electricity is currently flowing through. Ready? Here we go. Disconnect. Notice that it turned around and went the other way. Rather a lot of current to start with, but that lights it up really bright, but eventually it slows down and the light bulb goes out as this thing has expended its energy and discharged. Okay. The capacitor builds a charge. The inductor builds a magnetic field. All right, so now I want to take a look at what a capacitor and an inductor will do together. So I've got a battery down here, I've got a switch, I've got a capacitor, I've got an inductor and another switch. So when I flip this switch down here, it's going to allow the battery to charge the capacitor. I have also over here a current, an amp meter showing you a graph of the current. Right now nothing's flowing. When I close this switch, it's going to charge that capacitor. In fact, it does it really fast. Watch the graph here as I close it. Ready, set, go, bam. There's that instant, just there's no resistance here. Just charge that capacitor, and then all of a sudden the capacitor is charged. It says, okay, I can't take any more, and now the current stops. So there's that moment of a big spark that filled that capacitor, probably arced out this switch. But anyway, I got my capacitor charged now. I'm going to actually disconnect this. It will stay charged. It's got nowhere to go. So what I'm going to do is I'm going to allow that capacitor to discharge through the inductor. Notice the inductor is really just a straight piece of wire, and so it should be able to just allow it to go. There it goes. What happens? Whoops, I want to watch the current right here. What's happening? It looks to me like things are going back and forth. So the negatives are on this side, and now the negatives are over on this side. And then they go back the other way. So what's happening here? When this is charged, so for instance right now, we got the capacitor charged. The negatives and the positives here, all these electrons are going to try to flow out of here, through that. As the current starts to flow through that, a magnetic field builds up in here. So go, magnetic field building. As this is discharging, there's a spot here where I just missed it, but where that's not charged at all. So the capacitor is not pushing anything anymore. At this point, the magnetic field, which was being built by the current flowing through, now has to collapse because there's no more push coming in to keep it up. So as that magnetic field collapses, it starts pushing to keep the current flowing and starts pushing it back into the capacitor on the other side. So the inductor now is pushing back into the right-hand side. At some point, it has nothing left to give, and now the capacitor starts pushing backwards, and then the inductor continues up, so it's charged on this side. The capacitor pushes, the inductor pushes, and it comes back. There's this play between the two of them where you build the magnetic field, and then the magnetic field collapses, building the charge on the capacitor, but then it's not pushing anymore. The inductor is not pushing anymore, so the capacitor pushes back, builds the magnetic field again in the opposite direction, and then the magnetic field collapses, charging the capacitor in the other side. And what you get is a vibration. You get the current flowing back and forth. You ever hear a hum in the fluorescent lights? Yeah, that's because there's vibration going on. It's an electrical vibration. Anyway, we will look at the mathematics of this here shortly.